students, today I'll explain about one important property of D block elements, that is ability to form complexes. Okay, before going to this we should know what is a complex. So coming to the complex is a compound which is formed by the bond, coordinate covalent bond between a metal and ligand. Okay, so before going to coordinate covalent bond you should know what is a covalent bond. Here in covalent bond, two atoms shares electrons equally. Here A donates one electron, B donates one electron. By that they'll share equally and in order to form a covalent bond. But in this bond, ligand donates electrons to metal. Okay, after donating electrons, they'll share the electrons equally. Okay, that is the reason we'll call this as a covalent bond. Here ligand is coordinated to the metal. That is the reason we'll call this as a coordinate covalent bond. Here ligand is a donor and metal is an acceptor, as it is accepting electrons from ligand. Okay, now coming to this formation. So when compared to S and P block elements, D block elements will have more tendency to form complexes. Why? Because already we have discussed the oxidation states of D block. When we compare to S and P block, D block elements exhibits variable oxidation states from 1 to 8. So because of this variable oxidation state, they can involve in the variable complex formations. So many varieties of complexes it can form. So now we can see reasons. What are the main reasons to form these complexes? Because the first reason we can see, D block elements have high charged ions. So what is a high charge? So high charge is nothing but high oxidation state. Okay, if it is having high oxidation state, what will happen? High oxidation state means high positive charge. If it has high positive charge, it will attract all valence electrons towards itself, so that it will attract the ligand electrons towards itself. So whenever it has high charge, its size also decreases because of the nuclear attraction on the valence electrons. The size of the particular atom will decrease. Okay, so now they have vacant d orbitals to accept electrons. So D block elements also have vacant orbitals to accept the electrons from ligand. I told you already, ligand donates electrons to the metal. Metal is acceptor and ligand is a donor. So in order to accept those electron pairs, it must have a vacant d orbital. So D block elements also have this property of possessing vacant d orbitals. Okay, they also exhibit many oxidation states. Already we have discussed this point. Due to this, they can form various complexes. And what is the stability of complex? The stability of complex increases with the size of the cation, increases with the decrease in the size of the cation. So from left to right in a D block, size of the any element decreases. Whenever size decreases, I told you, this nucleus attracts the valence electrons towards itself, so that this nucleus also attracts the ligand electrons towards itself. If size decreases, it has more attraction on the valence electrons. So stability of complex also increases with oxidation state of the metal. Whenever a metal has highest oxidation state, it will have more positive charge, so that it can attract the electrons towards itself. So you can see FeCN6 minus 3 and FeCN6 minus 4. If you are calculating the oxidation state, you will get plus 3 here. And if you are calculating the oxidation state of this complex, you will get plus 2. Okay, plus 3 is more when compared to plus 2. So whenever the more positive charge is present on particular metal, it will attract all electrons towards itself. Okay, so you can understand this point. Now coming to one example, I am explaining this complex formation with one example. So Cr and H3 6 plus 3. Okay, chromium atomic number 24. It will have 3d5 4s1 electronic configuration, and next chromium oxidation state is plus 3. So what I will do, I will remove 3 electrons. Okay, if I remove 3 electrons, I will get 1 from here and 2 from here. So I will get 3d3. So 3d3 already I filled. This is 3d. After 3d we will have 4s. After 4s we will have 4p. So we are having 6 ligands. 6 ligands donate 6 pairs of electrons. Can you see? So here all vacant orbitals are occupied by the ligand 6 pairs. So totally ligand donates 12 electrons. Okay, 6 pairs of electrons to the vacant orbitals. So you can see here 3 unpaired electrons are present. So it is a paramagnetic in nature. Whenever any complex has unpaired electrons, we can call it as a paramagnetic. Okay, if I calculate the spin of this complex, what will get? Root over, already we know spin only formula, root over n into n plus 2. Okay, so if I substitute these 3 unpaired electrons, root over 3 into 3 plus 2. So root over 3 into 5. So root over 15. If you're calculating this root value, you'll get 3.87 Bohr magnetons. So this is a calculation of paramagnetic momentum or magnetic momentum. Okay, so this is about the complex formation.